Okay. Hello, everyone. Thank you for joining GeoScience and GeoEnergy webinar of 11th of June 2020 today. These webinars are hosted by my colleague and friend Sebastian Geiger from Heriot-Watt University and myself from TU Delft. We are especially grateful to our keynote speakers who have supported this initiative and to you all for joining us and combat work from home isolation. Please subscribe to our YouTube channel and help us spread the words. All previous lectures are available on our YouTube channel. Now to the lecture. We are pleased and honored to announce our keynote speaker of this week is Professor Mark Zoback from Stanford University. Well, Mark doesn't really need any introduction, but I will read a few lines about him. Mark is a professor of geophysics and the director of the Stanford Natural Gas Initiative at Stanford University. He has obtained his BSc from University of Arizona and MSc and PhD, both from Stanford University, all in geophysics. He co-directs Stanford Center for Induced and Triggered Seismicity, known as SCITS, and the Stanford Center for Carbon Storage, SCCS. Mark conducts research on in-situ stress fault mechanics and reservoir geomechanics. He has published 2 books, Reservoir Geo-mechanics, I'm sure all of you know, published by Cambridge University Press in 2007, which is now in its 15th printing. His online course, also entitled Reservoir Geomechanics, has been completed by over 10,000 students around the world. His new book, Unconventional Reservoir Geomechanics, was published by Cambridge University Press again in April 2019. Dr. Zoback has received a number of awards and honors. He was elected to the U.S. National Academy of Engineering and also in 2012 was elected to honorary membership of the Society of Exploration Geophysics. It's a pleasure and honor to host Mark this week. Please note his lecture will last about 35 minutes around that time, and then followed by questions and discussions. Like before, please type in your questions, text them in the chat room, and Sebastian will go through them after the talk. Mark, thanks once more. The stage is yours.
Well, thank you, Hadi, Sebastian. It's a pleasure to talk to all of you today. This morning, if you're in the Pacific time zone. Induced seismicity is a topic I've been interested in for a very long time. Just a brief personal note, when I was in graduate school, it was not all that long after the famous experiments at the Rocky Mountain Arsenal in Denver and the Rangeley oil field in Colorado. Those studies of induced seismicity were really, in modern times, the first time that scientists had the opportunity to apply kind of theories, ideas to real-world cases and actually test concepts that we had developed and were pursuing in the laboratory in a real-world setting. And that made quite an impression on me, and I was actually doing laboratory rock mechanics at the time for my PhD at the Geological Survey. And some of the principles in that those experiments, those 2 experiments, Barry Raleigh, Jack Healy, John Bredehoft, were all working at the U.S. Geological Survey and sort of later became my mentors during a postdoc. So this opportunity to study something of obvious importance and to sort of build a linkage between laboratory theories and real-world applications has been something that had a big influence on me from an early point in my career. I want to address 3 questions. One is, can we identify potentially active faults prior to produced water injection or hydraulic fracturing? Can we use physics-based models to guide regulatory aspects of oil and gas development when induced seismicity of concern? If we can help regulators, that's great. If we can't, they'll do what they need to do, try to protect the public using non-scientific principles. And how do we move beyond simple models and use more sophisticated models for example, incorporating poroelasticity or rate and state friction, and so on. And that's sort of a cautionary note I want to give at the end of my talk in the limited time this morning. These questions will be addressed in the research my group's been doing. Application of Coulomb faulting theory, incorporating uncertainty to identify active faults. We've extended Coulomb faulting theory with sort of a statistical technique pioneered by Serge Shapiro, and made some modifications, but basically it's the seismogenic index model he developed, and we've implemented it in Oklahoma. Cornelius Langenbroek, who worked with me for about almost 4 years, was one of Serge's PhD students. And I've been working with now a former PhD student, Lei Jin, trying to understand how to use poroelasticity to understand induced seismicity. You're all familiar with Coulomb faulting theory. And the key thing about Coulomb faulting theory is that it predicts both the relationship between the stresses and predicts the stress magnitudes and the stress orientation with respect to the idea that the frictional strength of pre-existing faults in the crust, and there are lots of them inherited over geologic time, controls stress magnitudes. In other words, stress differences can increase through various geologic processes. When critically stressed faults start to slide, that limits the stress differences in a predictable way. And we've been testing that in many places, and as we've had opportunities. The slide on the left is from the KTB site. Hans-Peter Harjes and I put this together based on a variety of studies. And basically, the difference between the maximum and minimum principal stress is shown here from direct measurements all the way down to 8 kilometers. And the dotted line is simply the predictions of Coulomb faulting theory for coefficients of friction between about 0.6 and 0.7, the kind of numbers we see in the lab. And you see Coulomb faulting theory and matches that those measurements extremely well. It says that the Earth is in sort of a failure equilibrium. The crystalline rocks, the granitic gneiss and amphibolites encountered in this wellbore. And to test that, we injected fluid at a relatively low pressure, just a few megapascals, and triggered a number of small earthquakes. So the crust is in failure equilibrium, and the law that describes that is Coulomb failure, and laboratory parameters, from small rock samples on the order of a few centimeters in size are actually applicable to faults in nature. The Coulomb faulting theory has been tested with respect to the orientation of the faults that are slipping. The work on the left is the relocation of very small earthquakes in north central Oklahoma. I'll be talking about this seismicity in more detail in just a few minutes. But Martin Schoenball and my colleague Bill Ellsworth at Stanford relocated all of these small earthquakes. Most of these are magnitude 2 and 3 earthquakes. The relocation allows them to define fault planes. And Oklahoma is a place where we've studied the stress field a great deal. In the lower right here, you can see the orientation of the maximum horizontal stress as determined by wellbore indicators, which is the straight line, and by inversion of the focal plane mechanisms, which is the heavy inward pointed arrows. They compare extremely well. It's about north 85 east. When you take the orientations of these small faults that were defined through the relocation process and you plot them on a Rose diagram, what you see is for strike slip faulting, which these principally are, the faults are plus or minus 30 degrees to the direction of maximum horizontal compression, just as one would predict from frictional faulting theory. Let's talk some more about Oklahoma. Oklahoma was an amazing laboratory. What we saw in north central Oklahoma was a process in which earthquakes, the red dots here, lit up over a few years over a very, very large area, hundreds of kilometers across. The blue X's are saltwater disposal wells. I'll talk about in a minute. The black X's are places where water is being recycled through enhanced recovery. Water is produced and then put back into the same formation. The earthquake story is shown along the bottom of the slide. Not much was happening. Prior to 2009, there was one magnitude 4 or larger earthquake per decade. By late 2015, 2016, there was one magnitude 4 or greater earthquake per week. And these, the great majority of people in Oklahoma live in the north central part of the state. And so these earthquakes were being widely felt on a weekly basis. And even though this is an area with a long tradition and history, working in oil and gas, an important part of the economy, these earthquakes are of considerable concern. It turned out, this is the answer, I'll tell you, show you some of the steps we took to come up with this. What was happening is at the time, oil was about $100 a barrel, a very high price. And some operators went to a few oil producing formations, which they had known about for many decades, but produced lots of water. And so they were never really economic to produce. So what they did is they drilled some very large volume disposal wells, not to put the water back into the producing zone like enhanced oil recovery, but instead to inject the water into a deeper formation called the Arbuckle Formation. It was very thick, porous, permeable, a kind of a karstic carbonate. It was even underpressured. So water could be disposed of in this zone by simply getting the water to the wellhead, and the water would fall in under its own weight at enormous rates. 10,000 cubic meters a day, and for some of the larger wells, and it just was a great place to dispose of all this fluid, all that salt water basically that was being produced. 2014 saw 700 million barrels. This is a little bit more than 100 million cubic meters. And so what had been a very convenient place to dispose of small quantities of produced water was now being hit with a tremendous volume. The pressure spread out over a very large area, found potentially active faults in the basement because the Arbuckle group sits right on top of the basement. This pressure would find a potentially active fault and penetrate that water pressure would penetrate that fault, and the earthquakes were occurring well below the depth of injection in the critically stressed basement. When we look at the sort of a map showing the flux of water, the geographic distribution of the quantity of water being injected through hundreds of wells, is a very good correlation. The background color is how much water is injected. The earthquakes are shown by gray. The larger earthquakes at the time we prepared this are shown by the brightly colored stars. And the state of Oklahoma, the regulators had defined these two big operational areas shown by these black lines. So spatially, there was a good correlation. Temporally, there was a good correlation. It was pretty clear what was going on. Now, could we have avoided injecting fluid near potentially active faults? If we knew that induced seismicity was a problem, if we knew a fault was present, can you determine whether or not that fault is potentially a problematic fault? And this is a study that Raul Walsh and I did and published in 2016. The answer is yes, if we know the state of stress, the orientation of the faults, the likely pore pressure perturbation. But we also need to incorporate the uncertainties of these key parameters. Now, just a minor change of subjects. Jens Erik Lund-Snee and I have just published a new generation stress map for North America. It appeared in Nature Communications about a month ago. The map incorporates something like 700 or 800 new orientations of stress. And then we're using 2,000 earthquakes to define relative stress magnitude. In other words, expanding on classical EM Anderson faulting theory by looking at these sort of intermediate sources of stress, and then using a concept my former colleague Bob Simpson pioneered of sort of quantifying relative stress with a parameter called A phi that maps into the color here. Well, the reason for showing you this is the Oklahoma work we've done is part of this. And basically these kind of intermediate colors are showing a strike slip faulting environment. It moves as we get up toward north central Kansas to something slightly more normal faulting. It becomes slightly more compressive in this area. Now, you see this very good, very consistent orientation of stress, both from the boreholes and the earthquakes at greater depth. We combine this with publicly available data on faults, and we then try to understand whether we can use Coulomb faulting theory, formally incorporate uncertainties, and discuss whether a fault is potentially active. And this is how we express the results. So this is east of Oklahoma City. This fault, segment 3, was responsible for a magnitude 5 earthquake in 2011. So we break up all the faults into so more or less uniform orientation, and then we assess the probability that a certain pore fluid perturbation, in this case we took 2 megapascals because that was the maximum conceivable, and that's a story that takes a little bit of time, so I'll just leave that aside for now. And we say, well, based on what we know, based on the uncertainties, what is the is this a potentially active fault? It's basically a screening tool. And we chose colors such that if the probability is on the order of 50% that it's problematic, we're going to paint that fault red. If it's less than 1%, we're going to paint it green, and then adjust the colors accordingly. And so, basically the fault that caused the earthquake shows up very nicely. Most of the faults are not problematic, but there are many problematic faults that have been mapped in the public domain, and we can identify them. Just as importantly, we can identify non-problematic faults. This is an outline of Oklahoma City. About 500,000 people live here. This 910 is part of a major fault system that goes on all the way well over 1 to 200 kilometers. Very old, very dead fault. And in fact, there are oil fields that are closed, up against this fault. But it had been hypothesized that maybe this fault was problematic. Well, it's a steeply dipping fault, nearly perpendicular to the direction of maximum horizontal compression. And basically, even if you raise the fluid pressure to the hydraulic fracturing point, which is what we're showing here, is fault segment 9 and 10, you can't make that fault slip, even by, say, hydraulic fracturing right into it. And so you can rule things out as being problematic simply because their orientation to the current stress field means they're not likely to move today. An important part of this is incorporating the appropriate uncertainties. This is hard work. If we allow parameters to vary over too wide a range, anything can happen, and therefore the value of the exercise is somewhat limited. And so in the appendix of our paper, Raul and I take some time to explain the assumptions we made and how these assumptions then get carried forward in the analysis. Does it work? Well, we now can look back at these thousands of earthquakes, and especially look at the larger ones, which are shown in yellow. The larger ones are important because the network is good enough that we can actually calculate focal plane mechanisms. When we calculate the focal plane mechanisms, in each and every case, we identify one of the planes that it would have been identified as a potentially active fault in 100% of the cases. The problem is we only knew about the presence of these faults after the earthquakes occurred. So the limiting factor in our ability to carry out this research in this case, it's not the stress state because of the oil and gas development. We were able to actually use data that was readily available and determine the stress state. It was very uniform in this case. It's not uniform everywhere, but we can map that. We can study that. But if you don't know the faults are there, this is not a methodology that can be used. Now, we incorporated this methodology into a freely available program we call FSP, Fault Slip Potential. Raul and I were developing this software, and then we were approached by ExxonMobil. They said that they were in fact doing the same thing. And so we combined forces, and ExxonMobil and Stanford released this software together. It's free. You can go to this URL. You can incorporate injection wells and faults. You can do some simple radial flow hydrology. I actually don't recommend this for reasons you'll see in a moment, but you can incorporate any kind of hydrologic information you have, and that's what I recommend, is that you do the hydrology separately, and then you import it into the program. We obviously do a geomechanical analysis, calculate the probability of slip at different pore pressure perturbations, and then point to the sensitivity of the analysis to different parameters. In other words, when you want to reduce the uncertainty, what parameters are most important in the particular application? And companies are using this software today in their applications for injection well permits in West Texas and other places, and we're really delighted. The regulators like it because at least it demonstrates that the company is thinking about these things and trying to be a bit proactive and avoid problems before they happen. Working with Peter Hennings at the University of Texas, we did a retrospective analysis of the earthquakes that were associated with unconventional gas development in the Fort Worth Basin. This is the Dallas-Fort Worth metropolitan area. 7 million people live in this area today. A number of small earthquakes had occurred during the injection of water associated with production of the Barnett Shale, getting natural gas from the Barnett Shale. So Peter and his colleagues greatly enhanced the information on faults throughout the region. We focused on the stress. We integrated our thinking on how pore pressure was perturbed and came up with a fault slip potential map. And basically, if you look at 2,600 kilometers of cumulative fault segment length in this area, the great majority of about a third of all the fault segments are completely non-problematic, and then the others are somewhat more problematic. If you look at the faults associated with the earthquakes, in all cases, one would have assessed that about a 20% or larger probability that this could be a problematic fault. And so, regulators could make up their own decision on where they drew the threshold. But again, the methodology seems to be working, and had it been done prior to the development of this resource, to the injection of this fluid, these earthquakes could have been avoided. Most of these earthquakes were pretty small and caused no significant impact, but it's a very populated area. The faults run right through the major metropolitan area, and it could have been a more serious problem, but the tools are now in place. Now, a very interesting thing happened in Oklahoma. The regulators finally sort of got the message that it's this large volume of produced water that's causing the problem. And so I started work with Cornelius Langenbroek on this, trying to adapt the seismogenic index model. The reason is that the regulators mandated a 40% reduction in water injection volumes. And the question is, was that enough? Was the 40% reduction enough? Was it too much? Could they relax that restriction after some period of time? So this is why we developed or sort of modified the seismogenic index model for application to Oklahoma. I'd been drawn to this model because there were a number of things about the model I really liked. First, it kind of presupposes sort of faults at many different orientations in the crust. Those faults are assigned a strength. Some of the faults are very weak. Some of the faults are very strong. Well, in my lexicon, a weak fault is a fault that's critically stressed, that's just at the right orientation to slip in the current stress field. And a strong fault is a fault which is very poorly oriented. So, you know, different words, but we're describing the same thing. And it's assuming that it's the diffusion of pressure from the injection site that is changing the pore pressure and triggering the release of the seismic energy that's already in the crust as a result of natural geological processes. I don't want to talk about this too much. There's not enough time, but basically it kind of, the method kind of decomposes the traditional Gutenberg-Richter law and separates out the anthropogenic effect, you know, how much you're injecting, from the geologic effect, and that's what's the seismogenic index of the crust. How many faults are there that you know, are critically stressed and likely or potentially able to induce seismicity. So if we look at earthquakes, we can that are being induced, we can decompose the anthropogenic from the geologic components, and that's to me, you know, very helpful. And it allows us to then, you know, use a statistical model to argue, well, you know, what's the annual probability of an earthquake of a certain magnitude? Well, the background rate is about a 0.1 annual probability for a magnitude 4, when, you know, of course, they were occurring weekly at the peak. And so these curves were moving to the right as more and more fluid was being injected, and then they start moving back to the left as the system recovers. And so Cornelius and I looked at the rate of earthquakes, which is shown in green, and made a prediction on how the system would return to normal as a function of time. And it is returning to normal as a function of time. But our work was criticized. We said, no, we're predicting too fast a drop off. And so using another model, some workers predicted a much more slow recovery as a function of time. And, you know, that's kind of what happens in seismology. Well, all branches of science, you know, it's this back and forth that makes us all better, you know, in the end. Now, one thing that was missing in this model is we didn't have a hydrologic model. What we used was what we needed was really the rate at pressure, that pressure was changing, and we used the rate at which the volume was changing, as a proxy for that. But the next step, with Matt Weingarten joining our group for a couple of years, is we developed a hydrologic model, and then we could actually talk about the pressure rate and compare it to the earthquakes. And so this was an important step forward. And, we could look at the pressure increases at the depth of the earthquake, 6.5 kilometers. It wasn't very large, just a few tenths of a megapascal, but enough to, trigger the seismicity. And you can see the excellent correlation between how the pressure is changing at depth and where the earthquakes occurred. And then with this model, we can move forward into the future and predict, how pressure is going to persist after injection continues. We assumed injection would continue at the same rate into the future, but we could have put any assumption into that. The other thing we did in this model is we disaggregated the seismogenic index. Instead of using one value for sort of north central Oklahoma and another value for this eastern part of the seismic area, following sort of the regulator on how they broke things up, we now had enough earthquakes in which we could actually define the seismogenic index on a finer scale. And what you can see here is an exercise we went through. If we had done this in 2014, if we had done it in 2015, if we had done it in 2016 or 2017, The yellow is showing the areas of high seismogenic index, and it's a logarithmic scale. And the dark blue is showing areas of low seismogenic index, much less susceptible to induced seismicity. And the general patterns that were apparent in 2014 are seen consistently through the data. And of course, over time, new areas kind of appeared, these areas over here, for example. But the consistency of these maps, as more and more data became available, told us that this area here, areas characterized by these yellow colors, were much more susceptible to produce earthquakes in response to the same perturbation. And it's kind of, it looks like a geologic map. It's consistent through time, and I think it was a step forward, and then allowed us to make predictions into the future. We know now how the pressure is likely to change if the injection rates don't change, and we know how the pressure is going to dissipate, and the rate of the pressure change is proportional to the seismicity rate in the seismogenic index model. And you can see that it fit quite nicely in 2015. 2018, the larger earthquakes occurred in a warm area, and we'll be able to look at this model through time. Okay, now those, Coulomb faulting theory and adding some statistics is pretty straightforward stuff, and it's working pretty well. But that's there are advances we could make, and I want to talk about poroelasticity because it's something we've been working on. And I'm going to make some cautionary notes about poroelasticity. And the first thing I want to do is point out that my students and I have been very engaged in trying to understand and utilize poroelastic theory. And there's one or two more papers here that are underway. So it's not like what I'm about to say should be interpreted to make me a poroelastic skeptic. But it's hard to use poroelastic theory. And there are three reasons. One is that the pressure and stress changes are in these heterogeneous reservoirs. We're talking about whether we're talking about crystalline basement or an unconventional oil or gas reservoir, extremely low matrix permeability and then higher permeability fractures. So it's a very heterogeneous matrix. The second is poroelastic parameters are difficult to estimate. And I'll show you some lab work we've done. And finally, the poroelastic stress changes turn out to be extremely small, especially compared with direct pressure transmission through permeable basement faults. Now, the theory is complicated, but there's one thing about the theory that you need to understand. And that is when you look at how fluid pressure couples to stress and stress couples to fluid pressure and try to, work with a fully coupled model, it turns out that the pressure gradients, which are related to flow, of course, is what creates the body forces that perturb the initial stress state, okay? So it's where the fluid is flowing, where the pressure is changing spatially, that induces the stress changes, the poroelastic stress changes we're interested in. This is from some work that's currently underway that Lei and I are doing. The application is really not very important. There's a well here. There's 5 hydraulic fractures. It's what's called a stage in unconventional development. And the only point I want to make is that if you were to inject, say, 5 megapascals for 7 days using realistic parameters, what happens is the changes in the stresses are very localized to the permeable pathways where the pressure is changing and where the flow is occurring. And so, it's not the kind of uniform pressure change and uniform stress change that we're used to looking in using poroelastic theory in, say, a more conventional reservoir where everything is sort of interconnected through a relatively high permeability. So it's a very, this is kind of an arbitrary geometry we put in for the point of calculations, but in the real world, where the heterogeneities are going to be extremely important. The second issue is the parameters we put into these models are very difficult to estimate. We carried out and published a very extensive set of experiments on the BO coefficient for some samples from the Bakken Formation, well-known unconventional oil reservoir in North Dakota and southern Canada. Without belaboring this, the BO coefficient, was studied using depletion or injection. There's some hysteresis, and under the exact same confining pressure and poor pressure conditions, the BO coefficient, would vary by a factor of 2, whether you are injecting or depleting, and so it's hard to know what the appropriate parameters are to use. These are very difficult experiments to make, as you can get some idea from the number of data points and the very methodical approach that we had to take. Finally, I want to emphasize that poroelastic stresses are very small. Here's a model by a group from the U.S. Geological Survey, Andy Barber and his colleagues. There are things about this model I like. They were trying to understand the biggest earthquake that was induced in the area, approximately a magnitude 6 earthquake, magnitude 5.9. Just to reflect back, these were map faults that were identified previously and would have been identified as potentially active faults, including this one where some of the foreshocks occurred, but the main shock occurred on this fault, which was on an unidentified fault and was later named the Sooner Lake Fault. Now, they modeled their poroelastic stresses associated with injection over time, but so they look at this over different time periods, how the injection was related, how the stress field changes. But when you actually look at what the mean stresses and the poroelastic stresses are doing, we're talking about kilopascals. So in the area of the earthquakes, the mean stress, and the differential stress, they're changing, say 10 on the order of 10 kilopascals. It's an extremely small perturbation. Now, if you think about pressure transmission directly through faults, and remember that, these basement faults will have damage zones associated with them, and these damage zones can be quite permeable, even if a fault core is relatively impermeable. Here's a picture of one of these damage zones. We can look at, oil fields being produced from faults in granitic rocks as a measure for how permeable these damage zones are. This is a study of the Subang gas field in Indonesia. It's a big granitic horse block here, and gas-producing sediments down in the Graben off to the west are actually propagating upward along faults at the margin between the granitic horst and the sediments, and a number of the faults are actually hosted in the granitic rocks, as shown. And the company found that drilling through these damage zones was an extremely efficacious way of accessing the gas that was flowing up these fault zones. How permeable are they? Well, some well interference tests, well 4, well 10, that were wells that were, actually encountering these big faults at the edge of the horse block, hosted in granite. These faults are communicating, pressure changes of a megapascal or 2 induced in one well are seen in another well within, a few hours when the fluid is able to communicate along these damage zones. So basically, if you were injecting, if this were not a producing field, you were injecting into a fault in the granitic basement rock in well 4, you're going to perturb the stress 5 kilometers away in just a few hours. And if the perturbation is a few megapascals here, you're going to get a few megapascals here, not a few kilopascals, a few megapascals. So it's these basement faults are really permeable and capable of transmitting pressure. And I think in the end, kind of coming back to what I said before, it's the knowledge of these subsurface faults that are the limiting factor in how predictive we can be. So just to wrap up, can we identify potentially active faults? Yes, if we know the stress field, which is knowable, but often we don't know enough about the faults. Can we use physics-based models to guide regulatory aspects? Yes, the Oklahoma regulators asked Cornelius and I if we would update our model monthly for theirs. We politely declined, but we told them that if they were considering changes in the regulations, limiting injection rates further or allowing more injection rates now that the earthquakes have subsided, we would run those models and tell them what we learned. And can we use relatively more sophisticated physical models? Absolutely, we have to. This is what research is all about. But it's hard in many cases to translate perfectly valid theories, things we know how to do, making that connection between the laboratory and our theoretical models and the real world can be really challenging as we try to take this research sort of to the next level. I'll stop there and thank you all for your attention.
Thanks very much for a very informative and inspiring talk, Mark. So now we start the discussion and question part of the webinar. Sebastian.
Yeah, thank you very much, Mark, for your questions. So please, everyone, if you do have questions, do enter them in the chat room, and I will be reading them out one by one.
Maybe we want to unclick the share screen, or so people see Mark.
Okay.
Okay.
Yeah. Now, yes.
Sure.
Now, yes.
All righty.
That's much. Thanks for the reminder. So the first question is from Suvik Sen, who said, how do you model SH-min in reverse faulting scenarios?
Okay. Well, and in the minimum stress is normally obtained through hydraulic fracturing. In a reverse faulting scenario, the least principal stress is the vertical stress. And so it's hard to get SH-min because it's greater than the vertical stress and you can't use hydraulic fracturing. In my first book, I spend a very large fraction of the book trying to talk about stress estimation. And basically the method you would have to use is to rely on things like wellbore failures. What is, are you getting drilling-induced tensile fractures in wells? Are you getting wellbore breakouts? Use things about wellbore failure that help you constrain the horizontal stresses, because you can't use hydraulic fracturing, which is our normal way of getting SH-min. And so it's a good question. It's challenging, but I go to great pains to sort of illustrate some of the techniques, but we do that. The other thing you can do, and that is if you're having earthquakes, if you invert the focal plane mechanisms, you can say something about the relative stress magnitudes. And for reverse faulting, SH-min is S2, the intermediate principal stress, and the relative stress magnitudes actually will map that minimum stress. Is it close to the vertical stress, or is it closer to the maximum horizontal stress? So you can get some inference from the earthquakes as well. But it's a good question. It's a challenging situation to work in, but there are methods available if you have observations from wells in an area, or if you have enough earthquakes that you can do a formal focal mechanism inversion.
Thank you. The next question is from Timur Garipov. Thanks you for a great talk. Could you comment on the temperature-induced stresses, please? Injected water temperature can be much lower than the rock temperature, may potentially change the stress state. Right,
and again, in my first book, we talk about these wellbore failures, and you have to make a thermal correction when you're trying to estimate stress from an observation of wellbore failure. This is, of course, a really big deal in geothermal settings when the cooling is really quite significant and can put the wellbore circumference into tension. And so that's sort of an environmental correction that you have to make when you utilize an analysis of wellbore failures. The larger the delta T, Under normal conditions, if you're not working in a geothermal area and you're working at modest depths, the correction is small. But when you're working in a geothermal area, the correction can be quite big, and you've got to do your best because if the wellbore is failing, it's a result both of the stress concentration, of the fluid pressure, in the well, the fluid, the mud weight used during drilling, and the thermal difference between the fluid temperature and the rock temperature. So it's an important correction to make.
Thank you. A question from Karim Abu Yana, who asked, thank you for the interesting talk. Did you consider earthquake interaction through stress transfer as a triggering mechanism in your models?
No, I didn't, and I think it's real. Obviously, when a fault slips, you get a stress concentration around that fault that perturbs the stress field in the immediate surrounding and could affect slip on a nearby fault. So this is a real phenomenon, but frankly, I think it's second order. When we reflect back and we find that to first order, the faults that are slipping are generally consistent with Coulomb faulting theory, what it's telling us is that the faults that are slipping are well oriented to the stress field. Now, the reason they slip may have been encouraged by this kind of stress transfer, right? But it would, like the fluid pressure, be a triggering mechanism, as the question implies. And ultimately, it has to be a fault that's, going to slip in this stress field to begin with. And so this can happen. I'm sure it does happen, but I think still we just using simple Coulomb faulting theory in a locally uniform stress field gives us most of the answer we need. But if you're actually looking at the exact sequence of a series of earthquakes, this triggering due to stress transfer is an important thing that should be considered.
Two questions from Artur Makhmutov. The first one is, how do you validate the results of your model? Do you compare them with field data, anything else, lab tests, etc.?
Well, I think it's very hard to scale lab tests beyond measuring material properties. But I tried to point out that the field tests compare quite well. The field tests of just simple Coulomb faulting theory, which planes are slipping are the planes we would predict to slip. And the rate of earthquakes in a given region in the context of the seismogenic index model are behaving well. Our predictions of earthquake rates in 2000, we did the work in 2015 and early 2016. We published a paper in late 2016, and the decline in the rate at which earthquakes are occurring in Oklahoma is sort of following the trend that we predicted. So we do our best to compare to field data. I tried to make that point that if someone asked me what I did for a living, I think the thing that characterizes what I focus on is trying to make that bridge between the laboratory and the field, and hopefully with some success. But my intention as a postdoc was to work in the field for a couple years and go back to the lab. I sometimes point out that my plan was fine. I'm just 40 years behind schedule. Actually, I do have a lab, but it's a good question. I think we have to we have to keep testing what we do against field observations if we're going to argue that these, whether it's pure theoretical work or laboratory measurements, are applicable to the real world. So we try our best.
Thank you. I'm just going to skip one question here and then come back to Artur in a moment. But there's a related follow-up question from Alex Novikov, who again thanks you for an exciting talk. Ask if you could please comment how Coulomb faulting theory and friction loss change of scale from the lab or core scale to the reservoir scale.
Well, I think that's the amazing thing. It's the thing that struck me during my PhD work with the Rangeley and the Denver earthquake studies is, the argument was that laboratory-derived coefficients of friction on, centimeter scale samples were applicable to faults in situ. And it was like, really? I mean, can you really argue? And a number of decades down the line, we're finding remarkable consistency. We find that consistency in other ways. So, for example, in the of course, in the United States and Canada, now in China and Argentina, the development of these unconventional reservoirs is a very big deal. And we're working with clay-rich rocks. And something we know from the laboratory is that the coefficient of friction tends to go down a little bit with clay content. And as clay content exceeds about 30%, you go through a transition using rate and state friction between velocity weakening and velocity strengthening. In other words, the high clay rocks, when you predict them to slip from Coulomb faulting theory, they're not predicted to slip unstably. In other words, their velocity strengthening. The faster they slip, the stronger they become. And so you would predict that those faults would creep aseismically and not. And we actually see that in a number of cases. So it's another example in which at least the inferences we would make from laboratory data, at least to first order, are consistent with what we see in the field. Now, that said, a lot of the other parameters that come from rate and state friction, weakening distances and things like that, are really hard to translate from centimeter scale to the kilometer scale. And so, it's still a struggle to know how to do that scaling. So to first order, a lot of the primary parameters we work with are scaling quite nicely, but there's a limit in how far we can push that. And, if I had not singled out poroelastic theory and had talked about rate and state, I could have made similar statements. It's real, it's happening, it's a physics we need to understand, physics we need to apply. But when you actually look at the laboratory data and ask ourselves how we're going to scale up to the field, it's a hard thing to do. So it's a good question.
So staying along the lines of scales, sorry, question up here. Florian Dost asks, could you elaborate more on your argument with respect to poroelasticity in fractured rocks and the strong heterogeneity in pressure? Isn't this just a matter of applying the concepts at the right scale? Absolutely correct.
It is. I guess what my comment was meant to say is you've got to put in the correct parameters that define the heterogeneity. And if you can do that, then the theory is fine, and or at least we think it's fine. You could then test that theory in situ. So you have to characterize the rock at the appropriate scale. So I totally agree. But as anyone who's tried to do this, in any kind of underground laboratory or anything else, it's a difficult thing to do. But if you can do the characterization at the appropriate scale, then poroelastic theory is available to you. And the complexities I talked about are straightforwardly dealt with. But it's that detailed characterization that's important.
Thank you. So finally, we come back to Arthur's second question. In Groningen, they stopped gas production due to seismic activity and earthquakes. Does stopping production always help you in such cases?
Well, I've looked at Groningen a bit, and the method by which reducing pressure triggers slip-on faults is quite different than how injecting fluid. Rather than the decrease of the effective normal stress, what you're doing when you're getting earthquakes from decreasing pressure in normal faulting environments, which is an important point to point out, and which is applicable to Groningen. The rate at which the minimum horizontal stress changes poroelastically, with the pressure change, it's called the stress path, defines normally a stable situation. In most reservoirs, the way pressure and stress evolves makes faults less likely to slip. But in my first book, I talk about a field in the North Sea, the Valhall field, where in fact, it's very much like Groningen. The stress path brought the field closer to normal faulting failure as production went forward. In that case, what happens is you bring the faults closer to failure, and then stopping production, basically you're no longer perturbing the system. Okay, that's good, but those faults are sort of already been brought to the failure, to the failure level, and so it's not going to be as dramatic. Now, I think if production is stopped at Groningen, then that I think the seismicity will subside, because the perturbation rate will subside, and therefore the seismicity rate will subside, but it won't be as dramatic. It'll probably, there'll probably be earthquakes going on for quite a while afterward. So it's a different phenomenon. With Groningen, my personal view of what's happening is not necessarily shared by the operators. And my personal view is that had it been identified earlier, in the evolution of the field and the onset of the seismicity, there might have been some remedial steps. I'm not sure. But things basically progressed quite a ways before they were, really identified and looked at seriously. And so a lot of those faults that had been close to failure but not active. I mean, earthquakes were, occurring at, at least, a modest background rate throughout that part of North Central Europe as a natural process. That perturbation has now occurred, and how you get back to the background rate is a tough question.
Thank you. Now, another sort of field scale question is from Vashwardhan Verma, who asks, now that CCS projects are being pushed all over the world, what difference do we expect to see between CO2 and water injection in terms of induced seismicity?
Well, very good question. Pressure is the problem. So if you're generating pressure through CO2 or you're generating pressure through water, of course, they'll behave different in the pore space, but it would be predictable. There's good news and there's bad news, or cautionary news. The cautionary news is with CO2 injection, don't repeat what we observed in Oklahoma. For example, if the Arbuckle Formation had been used for CO2 sequestration, because it's thick, porous, permeable, good shale cap rocks, okay? That pressure change in the Arbuckle due to CO2 due to CO2 injection transmitted into the basement, okay, would have had the same effect. So that tells, Oklahoma tells us what not to do. So don't find saline aquifers, for example, that are the basal unit sitting right on top of the basement, okay? Because pressure transmission into the basement is important. So you need a bottom seal as well as a top seal. The good news is that in many places in which we're considering CO2 sequestration, the rocks we're talking about sedimentary rocks above and below the injection zone. And when you, in many of these sedimentary rocks, the rocks are more ductile and less brittle, and you're not at that incipient failure point. And so you have more latitude. And we're doing some work right now with a company trying to identify depleted oil and gas reservoirs in the Gulf of Mexico area as potential CO2 storage sites. And, there's lots of sedimentary rocks below the injection zone, so we're not transmitting pressure into the basement, so that's good. And secondary, a lot of the rocks in the sequence are very ductile, and they're not at the frictional failure limit, and that gives you some much more latitude. And it turns out that some of these rocks that make a good hydrologic seal make a good geomechanical seal, because they're clay rich, they're ductile, they have very low permeability, Therefore, they make a good hydrologic seal. But that clay-rich ductility means the stresses are much less anisotropic, and it's harder to induce fault slip. So, there are, as we look at potential CO2 sequestration sites, we see things to avoid, but in many cases, the geologic setting is really quite attractive because of the ductility of the rocks involved. And so, but the physics, there's a lot of similarities to the physics, which I think is what the question was all about.
Thank you. I'm going to take a couple more questions. I think then we're sort of slowly running out of time, and there's some questions around how more complex models may help us to make better predictions. So one is from Musa Hosseini Mir, who asked, would the use of more complex models, say including phoroplasticity, help for better predictions? Or, and he follows that up with a follow-up question, is it necessary to include nonlinear friction coefficients?
Well, right now, I think the explosive term in the question is the word prediction. And I think we should use these more sophisticated models. If you want to use nonlinear friction, if you want to use rate and state friction, if you want to use poroelasticity, are mostly helpful retrospectively when we know what happened and simple theories aren't adequate for explaining it. I think it's very hard to use these sophisticated models in a predictive mode because we simply don't have enough information. And so I tried to choose my words carefully. I may have failed to do so. I'm not critical of more sophisticated models. We need more sophisticated models, but I think when we do, I think we have to, as scientists and engineers, I think we have two parallel, equally important roles. One is we have to do the kind of science and engineering that's of direct benefit to regulators, the public, the companies in their decision-making in a predictive mode. And secondarily, but just as importantly, we want to understand as much about the process as we possibly can. And what I didn't say, but what I was sort of implying is we pursue both paths, but the more sophisticated models, because we have to input, a lot of complicated parameters and characterize it, with some sort of numerical model, we reserve it for that second path, for that path where we're trying to, achieve as best an understanding of what's happening in the subsurface as possible, rather than, because, as anyone knows who's worked with these models, what you put in determines what you get out. And, and that's okay in retrospect when you're trying to explain a complicated situation, but it's hard to defend when you're trying to be predictive. And that's sort of my story, and I'm sticking to it. So,
so we take one final question, and again, it's about slightly more complex models. Milad Nadelu asked, says, thank you for your impressive talk. My question is, did you consider hysteresis behavior or inelastic deformation during injection depletion processes? This behavior could this behavior influence seismicity?
Yeah, I went through it very fast, but the Ma and Zoback paper 2017 in JGR talks about our work with the BO coefficient, and it's elastic. Our perturbations are small, the rocks are strong. There's no real permanent deformation of the rocks, so the rocks are not inelastic, but there is hysteretic behavior, and the volumetric strain associated with pressure and changes, that we measure volumetric strain to compute the BO coefficient. That is different in whether we're injecting or depleting, and that leads to a different BO coefficient. So in that one context, yes, we do, and it's not due to inelasticity. And if you look through that paper, I'm very proud of that paper, proud of the work that Xiaodong Ma did. It was a remarkable laboratory set of experiments, very carefully done. But the hysteresis is definitely there, and it raises this question that we have to be very careful with the BO coefficient. I singled out an extreme case, but under the exact same pressure and poor pressure and confining pressure conditions, we got values of the BO coefficient, something which is sort of fundamental to pore elasticity. We got values that differed by about a factor of 2, which is quite considerable. So it's another good question.
Okay, so thank you very much to the audience for all the great questions, Mark, for answering them so diligently. And I hand over back to Hadi for some final comments.
Thank you very much, Mark, for this very inspiring talk. And we could run the question and discussion still longer, but I guess you just woke up. It's 7 a.m. when you started.
I'm awake.
So thanks to the audience. I would like to mention that our next speaker is Bill Rossen from TU Delft. Bill will talk about flow and transport in porous media with foams. Please stay tuned, stay all happy, healthy, and we see you all next week. Mark, thanks once more.
Of course.
It was our pleasure.
Bye.
Pleasure. Bye-bye.